Okay. I would like to go and review the questions on the midterm, the answers pretty quickly. Okay. The first question, it was a backtracking question where you had to construct all permutations where there was never a leap of more. You have all permutations on n items where there was never more than a leap of k between successive elements. Okay, so in this case, here there's a leap of 2 over there. Here there is a leap of 2 over there. When there is a leap of at most k, then it's called a k-stepping permutation. These are not 2-stepping because here's a leap of size 3 and here's a leap of size 3. How do you use backtracking to efficiently construct all of these permutations? Again, I encourage you to write your solutions in terms of construct candidates is a solution and process solution. The way I would be dealing with this is I would deal with this a lot like I was generating any permutations. I would build a solution vector where there's n slots and build my permutation one after the other. Okay, good. I think I'm getting a fire drill, but it's only a testing thing, I think. So hopefully I won't have to abort. But what is the issue here? The issue is that I want to, when I generate my, how would I do it? When I'm generating my kth thing, I would want, first of all, I'd want, if I'm generating all permutations, I want is a solution to be the same, probably meaning have I filled up the array. Process solution would mean to print the solution. Okay. The heart of doing this efficiently are what are my candidates for the kth position? And I would say that there are 2 different criteria. It's the items 1 through n minus anything a1 to ak. I can't use an element that is I've already used, plus also minus what? Any element that is, if this is going to be a of k, I want only elements from, I mean, let's call it a of j, just to keep my notation similar. But basically, I want any element that is, if it is minus anything from 1 to a j minus k minus from a j plus k to n. So these are the, I want to delete the elements that are too big, small relative to the kth element and too big relative to the kth element. Any questions about that? The only candidates for the next property can't have been used and have to have been within k elements plus or minus of the last element so far in the permutation. Any questions? Some people may have constructed all the, some people may have just constructed all permutations and then used process solution to throw out the ones that you don't need. That is, I guess, correct, but it fails the efficiency test, okay? Because again, if we assume a world if k is equal to 1, there are only 2 different solutions, the sorted order and the reverse sorted order, okay? And if you have to construct all n factorial permutations to find that out, that is bad. Any questions about that? Any questions about what we're looking for here on this backtracking problem? Okay, good. Next question says you're given a dictionary and it contains, which has m distinct words. So I've got a dictionary D that consists of m words. each of which is of length at most k. Okay. And I am giving you a target string S, okay, which is of length n. And I want to know whether this target string can be made as a concatenation of dictionary words. And some of them are, and some of them aren't. Okay? And this should smell to me like a backtracking problem. Okay? The backtracking problem, not a backtracking problem, might smell like a backtracking problem, but then you've got the wrong sense of smell. The right thing is it's got to be a dynamic programming problem, okay? Namely, what is the idea? If the string can be represented by words, what is the criteria as a concatenation of words? It has to end on a concatenation, and everything before that has to be concatenable. So my definition is I am going to define a function. Let me call it, what letter do I want to call it? Who knows? Let's say that I want to define a function C of I, which is going to be true if and only if S sub 1 to I can be expressed as a concatenation of dictionary words. Now that I've written it down, now that I know what my function is, can I define what that function is? And I'm going to say C sub I with a recurrence. C sub I is going to be true if, basically, C sub n is going to be true if what would I like to say? If let's say S, my dictionary word K, okay, is equal to from my string S ending at n, from n minus the length of dk. My notation may be bad, but what am I saying here? If the last characters of my string match a particular word, okay, dk, and okay, C sub n minus the length of dk is equal to true. Okay, so what am I saying? This says I'm going to go, if every word in the dictionary, if I can end, I'm going to go through every word of my dictionary and align it to the back of my string. Okay, for any one that matches, if okay, it matches the end, and my function C is true up to the point where it matches, then C of n is true. This is what my condition is. Okay? Any questions about that? Okay? About what that idea is? I may have written it not very clearly. That's why you should explain this. You would have to write down an explanation in English if you understand my notation. But the idea here is not that complicated, I think. Any questions? Okay, any questions about this solution? What's the boundary case if we understand my solution here? Does anyone want to tell me my boundary case? What is my boundary case of this recurrence? Somebody's got to see it. Okay, C sub 0 is equal to true. Right, an empty string of length can certainly be expressed as a concatenation. Okay? So what do we know? Is it a graph algorithm? No. Is it a dynamic programming algorithm? Yes. What is the running time of this thing? I'd say it is always the number of boxes times the time per box. What is that going to be? The number of boxes is n. What is the number of what is the number of things I have to test here? Well, to fill each box, I'm going to take each of my n dictionary words. How many dictionary words did I have? M dictionary words. And for each of the M dictionary words, I'm going to align it to the back. Okay, that's going to take time proportional to its length and, to do that test. And either it matches or it doesn't. If it doesn't match, I move on. If it does match, I check this out. It's going to be, basically, I'm going to be trying this for a total of M words, each at most N. The time per box is going to be M times K. The total time is order K, M, N. And that's there. Any questions about this one? Okay. Okay. Any questions about this dynamic programming problem, or do people see where it comes from? Okay. This is going to remember what's actually realizable, and then we're going to just check to polish it off by doing that search. Any questions? Okay, good. What is the third problem? It asks you to play gotcha solitaire, where you've got n cards and m pairs, such that card I must be played before card J. And you play by picking the cards, by ordering the cards. So you can, put all the cards down. You want to put all the cards down so that all the gotcha pairs go from left to right. Okay, that's kind of what this is telling you. Give me an example of a pair that doesn't have a solution. Well, 1, 2, 2, 1. There's no way to order that two-deck card, those two cards, so that it satisfies all the gotcha constraints. Now, how do you solve this? Well, this should smell very similar. This should smell exactly like topological sort. Okay. And if you see that, then you say, yes, this is a graph algorithm. It's not a dynamic programming algorithm. Just do a topological sort on the gotcha pairs. And the order you get are the order of the cards you want to play. So do a topological sort, and you pay that much time for it. Any questions about this problem? Any questions about anything on the midterm? Going once, twice. Again, if on any of these written questions you had a correct solution that we marked wrong, we are willing to look at it. Again, we are uninterested in complaints like, oh, it wasn't so as incorrect as the number of points you had. Only if you can do it, do it. Okay, there's a question of, can problem 3 be done by backtracking? And the answer is, could you have done backtracking for this? The answer is, you could conceivably have constructed all n factorial permutations and done that kind of thing. But that's obviously an exponential time thing. Okay, and this thing is this thing. Any question? Could you do this thing with dynamic programming? I don't see any reason why. This is a simple topological sort. Okay, there's all kinds of heavyweight things like exponential search you can do, but that's not the way to this is one that has a simple, efficient algorithm There was no exponential possibilities here. Okay, so clearly that's not a solution. At least not a solution to receive a lot of credit. Any questions?
For number two, could you also use backtracking by constructing all the subsets?
Could you have done backtracking? The answer is yes, but again, it would be a exponential thing. It would be an inefficient thing. Okay, it should be clear. This is one where you can do this thing in, I said efficient algorithm. The word here is efficient. Okay, if you do it by backtracking, yes, you could. If you think about it, any dynamic programming thing is defined by a recurrence relation. You can always do your recurrence relation by exhaustive search, if you want to run up a bill on a cloud or something like that. But if you want to do it efficiently, you save the partial results. And so this needs to be done by dynamic programming to be efficient. Okay, any questions? Okay, any other questions about the midterms or anything like that? This was the criteria. I know that this is a time of the, in a strange semester when everyone is stressed out and yada yada. Don't get too stressed out about things. Again, the people who I'm concerned with were the people in the 30s or below. If you if you're in that category, you may want to come and try to chat with me during office hours or something like that. But if you're up in here, you're certainly going to get your passing grade, and that's not going to be a problem. Okay, assuming you do everything else in a comparable manner. Any questions? Okay, any questions? Okay, if that's so, I'd like to move on to the real topic of today's lecture. Let me see if I can get that going. Bang.
Actually, Professor, I'm sorry, I forgot to ask, do you know what the standard deviation
Okay,
is?
I'm not hearing you. Say this again.
Do you know what the standard deviation was?
So I don't know what the standard deviation was. If the TA is listening and wants to tell me the standard deviation, if you're really certain about it, you could compute an estimate of the standard deviation by looking at the, assuming the number of people or everybody's in the center of their bin. Okay. But anyway, okay. Let me go and get to the lecture for today. Okay, hold on. Okay, so what I'd like to talk about today is, one of my favorite topics in the world, and I actually think the students generally like this topic. Okay, it's been a long semester; people are beaten down in many ways, but NP completeness is a kind of one of the really kind of important ideas in computer science. Not even completely just computer science, actually. In the real sciences, people, there are relationships between things like complexity theory, things like, NP completeness, and how nature works and all kinds of things. NP completeness is kind of this concept about something about the way the world was built. However you think the world was created, they created it with NP completeness. They didn't necessarily create it with dynamic programming, but there is this notion of hardness, of problems, that is a kind of fundamental part of the world. And I think that it's something that people look at and tend to, at first, looks scary and ridiculous. But we're going to go over things again and again over the next couple of classes. And I think people will develop an appreciation for how exciting this concept is and, how it can work. But let me start just to motivate it by a practical concern, which is suppose, let's say, you are hired, okay, and you are going, somehow by some miracle, you get a job after this class. And they hire you to go do build, let's say, a algorithm, a fast and efficient algorithm for something like the bandwidth problem. And you will sit down at your desk and you're going to try to find a fast algorithm that always finds a solution, the right solution to the bandwidth problem. And you're going to fail over the next couple of weeks. And then the boss calls you into the office. What can you say to the boss? You could confess to the boss, I could not find an efficient algorithm. Okay? Okay, I guess I'm too dumb to find an efficient algorithm for this problem. What is bad about that kind of a confession? Okay? The boss is likely to fire you or something like that. They didn't want to hire somebody dumb. Much better would be if you could do something like we did early in the semester when we talked about decision trees for sorting. Maybe you could prove there absolutely positively cannot be in this universe a fast algorithm for bandwidth. Okay? Now that would be good. The boss can't fire you, okay? Because now he's asking you to do something you can't do. But in fact, it's very hard to do really good lower bound proofs, and not very, very few problems beyond sorting have interesting lower bound proofs. It's actually kind of a scandalous thing in theoretical computer science. Okay? But there is something that you can prove to the boss very, very easily that is almost as good as that. You can prove to them that although you can't find an algorithm, fast algorithm for this, nobody else in the world can. I might say, you can't hire Skeena to do it. Skeena can't find a fast algorithm for this problem. You can't hire Richard Karp. He won't find a fast algorithm for this problem. That you can basically come up with a way of proving that no one in the world can solve your problem, even if you are the first person in the world to think about your problem. That's kind of an amazing thing, okay? You could imagine if, you could prove that, you might say, well, we could prove that Skeena can't solve the bandwidth problem. If you could Google on the web and you find the text, Skeena saying, yeah, I can't solve the bandwidth problem, okay? But what's interesting is through NP completeness arguments, you can prove that problems, no one in the world knows how to do this, even if you're the first person to ever try, okay? And that you can make a proof or argument like that is kind of an amazing thing. And it's also amazing that once you understand these techniques, they're actually not that terribly impossible to apply. So what is the theory of NP completeness, or what is the issue? The issue is many times this semester, we have seen problems where there was no efficient algorithm. We talked several times about the traveling salesman problem. Given a graph, find the shortest path that visits all the vertices in a graph. Not the shortest path from A to B, but the shortest path where you visit all the intermediate cities. Okay? We talked in here about vertex cover at times. We talked about independent set, okay? And I think some of the homeworks and things like that, okay? So it turns out that for all these problems, no one in the world knows an efficient algorithm. And no one knows a lower bound proof quite like the one that I showed you for sorting, okay? Which is an argument that there simply can't be a fast algorithm, okay? What the theory of NP completeness does, it gives us a way to show that seemingly different problems are really the same thing, okay? And so if you can solve one, if they're the same problems, if you could solve one, you could solve the other. If they're the same problems, you can't solve one, that means you can't solve the other, okay? And that is the basic idea behind NP completeness. Any questions so far? Still been talking at the abstract level. But the next two slides are the idea about NP completeness, okay? And so if you understand the next two slides, you will understand everything, okay? But the next two slides are more subtle than they look, okay? what I want to show you is an algorithm to solve the Bandersnatch problem. What is the Bandersnatch problem? It's just the name of a problem. Maybe it's traveling salesman. Maybe it is independent set. Maybe it's shortest path. Maybe it's, I don't know what it is. But this is an algorithm that to solve the Bandersnatch problem. Take the Bandersnatch problem happens to work on an input of G. Our Bandersnatch algorithm works by taking that input G and translating it into an input Y, which is the format for the Mobility problem. What is the Mobility problem? It's another algorithm problem. Maybe it's shortest path. Maybe it's maybe it's edit distance. Maybe it is what other things did we discuss in here? Maybe it's minimum spanning tree. Who knows what it is? Okay. Then we call mobility a mobility solver, a subroutine for solving mobility problems on this new translated input Y. And we return the answer, mobility of Y, as the answer to Bandersnatch of G. Now, if we did this translation in a way that Bandersnatch of G always equals mobility of Y, then this is a correct answer, a correct algorithm. Does everybody see if we did this translation in a way that Bandersnatch of G is the same as mobility of Y, if I have a fast mobility solver, I can compute mobility of Y, and if the answers are the same, I can return mobility of Y as the answer. Any questions about that? If Bandersnatch of G is the same as mobility of Y, then this is a correct algorithm, because the answer of Bandersnatch of G is mobility of Y, and that's what I'm returning. Okay? Any questions about this algorithm? An algorithm where we translate, one problem into another is a special type of algorithm we're going to call a reduction. Okay? Any questions? If you looked at my edit distance notes, you probably did kind of see a reduction before. Remember when, if you looked at the thing about longest increasing subsequence or longest common subsequence, did you see that once you knew how to solve edit distance, basically these two were special cases. If you had an edit distance solver, you could solve longest increasing subsequence or longest common subsequence, if you remember those problems from the book or the notes. Any question about this algorithm or what it kind of means? Okay, maybe it still looks blank looks or okay at this point. The important thing is that when you have an algorithm like that, they're assuming that translation happens in time Pn. That algorithm could mean one of two things. If mobility runs in P prime n time, then I have a fast Bandersnatch solver. Why? If we go back to my Bandersnatch algorithm, if translating this took P of n time, and the mobility solver took P prime of n time, returning the answer took just constant time, this would give me a Pn plus P prime n algorithm for solving Bandersnatch. So if mobility is fast, then this algorithm gives you a fast Bandersnatch. But if you know that there is no way to compute Bandersnatch faster than P prime n, then there is no faster way to compute mobility than the lower bound minus the translation time. Okay? Because if I had a fast way to compute mobility, this would give me a fast way to compute Bandersnatch. If I know absolutely positively that there is no fast way to compute Bandersnatch, and I give you an algorithm like this, what do we know? If the translation, which is typically, a fast just translating, reformatting the input, if the translation takes p prime n time, and the total, and Bandersnatch takes at least pn time, let me write that down, at least pn time, then mobility must take at least pn minus p prime n. Okay? Any questions about that? This is the reasoning step, and I want to make sure people get it now. Although I'm going to give you more chances in coming days. What was the idea? If there is no fast way to do Bandersnatch, I swear to God, there is no fast way possible, faster than p prime n time to compute Bandersnatch. Then if I have an algorithm here which solves Bandersnatch by doing a translation and calling a subroutine, if I know how fast, if the translation is fast, if Bandersnatch must be slow, then this algorithm proves that mobility also must be slow. That is the idea here. Okay? Any questions about that?
Professor, why is it p of n minus p prime of n instead of p of n plus plus p prime of n?
Okay, let's go back to what I was saying here. Let's see if this makes sense. So maybe I'll erase it a little bit. Okay, now let's look at this a little subtle. Okay? Now, suppose my translation took p prime n time. Okay? Now, this is the time. Okay, suppose my translation took this time. This is the translation time. If I have a fast mobility solver, I can solve it in translation time plus execution time. Now, when I translate the size of my problem, the size of my input is going to get bigger, right? It's possible that when I translate it, the size of it is going to change. When, let's say, you translate files from zip format to the big format, does everybody believe that it is, what you call it, it might get bigger, the size might change? So that's why I'm changing the variable here. Okay, well, that's maybe a little more subtle than I want it to be. What is the key idea here? Suppose I know that this is a worst case lower bound on the running time. This is a worst case running time lower bound. Suppose I know that any algorithm to solve the Bandersnatch problem has to take at least 2 to the n time. Okay, let's make this clear. Suppose I tell you that Bandersnatch must always be greater than or equal to something like order 2 to the n. Okay? There's no non-exponential time algorithm for solving Bandersnatch. Suppose I know that. Suppose you give me an algorithm like this that solves Bandersnatch by doing a fast translation and then calling a mobility solver on this translation and returning that. Suppose I give you a correct algorithm on this, and I give you a bound that says the running time here has to be greater than 2 to the n. If my translation took order n time, Let's make it n squared time just to be fast. What does that guarantee? That means that there is no possible way to solve mobility faster than 2 to the n minus n squared. Okay? Any questions about that? Do people see why? If I guarantee you there is no way to solve this thing fast, and I give you an algorithm for it that would be fast if there was a fast mobility solver, what does this algorithm prove? It proves there can't be a fast mobility solver. So everybody kind of see that. That's the logic here. If I show you that there is no possible fast algorithm for Bandersnatch, and here is an algorithm for Bandersnatch that would be fast if mobility could be solved quickly, what does that mean about what you call it? What does that mean about mobility? Okay. Means that there can't be a fast algorithm for mobility. What if I absolutely swear to you, okay, that there is no possible place, a way for you to get $1 million in the next minute? And suppose you are standing next to me with a gun, okay? And you say, give me your wallet. What do we know about what's in the wallet? If there's no possible way for you to make $1 million in the next minute, and you're hovering over me with a gun, give me your wallet, Skeena. What do you know that's in my wallet? Okay, it's less than $1 million. I'm going to break that to you gently, right? And that is the kind of reasoning we're going to be using here. Any questions about that? Any questions about the Bandersnatch reasoning here?
So just to kind of do it in reverse, if we go back to that slide, the time to run mobility plus n squared must be greater than or equal to 2 to the n?
Well, the time to run mobility, that's exactly right. The time to run mobility plus n squared has to be greater than 2 to the n. That's exactly right. Okay?
Perfect.
And that's why I have a minus here. That's the exact, kind of, you did it. Mobility plus time plus this has to be less than this. Okay? Has to be greater than this. Excuse me. That's the argument. If this is hard, and if this will solve Bandersnatch, mobility time plus translation time has to be greater than 2 to the n. Any questions about that? Okay. Any questions about this reasoning? Okay, you will see those slides again, but I encourage you to think about that. Okay, now I have a Twitter account. I encourage you all to follow me. It's, and the best tweet I ever made was this one. Do I follow back? No, I'm not going to be looking at you guys at all. Okay, any questions? Okay. But what was my tweet? I once said that an NP completeness proof ensures that a dumb algorithm that is slow isn't a slow algorithm that is dumb. Now, why does that mean something? Let me think, why do I feel profound about this? What is a dumb algorithm that is slow? An algorithm is slow, that a slow algorithm is only dumb when there is not a faster one. Okay? Isn't that right? Okay, if you have a slow algorithm for the backtracking, for the for bandwidth, if you can't find a fast algorithm for it, all you have to settle for is backtracking. Is that a dumb algorithm? It's not a dumb algorithm unless there is a faster one. Okay, so a dumb algorithm that is slow is a simple algorithm like backtracking that happens to be slow. A slow algorithm that is dumb is an algorithm where you are spending much, much more time than you should be spending. Okay? If I have a slow algorithm and my problem is hard, then if my slow algorithm is a problem that if I have a slow algorithm on a hard problem, that's not dumb. If I have a slow algorithm on a problem that can be solved efficiently, that is dumb. How do you tell the difference? If I can prove that my problem is hard, then I know I can't do better than a slow algorithm. Okay? Any questions about that? Okay. Again, we're still at maybe an abstract level. Any questions? Okay. So now let's be a little bit more to do what we're going to need to do now. That's the high level thing. You need to figure out and try to understand that. We'll go over it again next class. But what is the we have to be a little bit more formal about what we mean by problems, because now Bandersnatch and Mobility were problems. What is a problem? A problem is a general question, okay, where there are parameters and conditioners for what's a solution. So when I talk about a problem here, I mean something like traveling salesman. Traveling salesman takes as input a graph, and it asks to find a tour, an ordering of the vertices that minimizes the sum of the edge weights on the tour. Okay? So when I talk about a problem, I'm going to be talking about a general instance. Okay? Any questions about that? Okay? When I talk about an instance, what I mean is the input to a problem. This graph is an instance of the traveling salesman problem. It is an input, it's a graph. An instance is the input. The problem is the definition of a problem. Okay? Any questions about what the difference is between an instance and a and a problem? An instance has a solution for a given problem. In this case, the minimum tour happened to cost 27. Okay? But problems are abstract things. Okay? Instances are the inputs of our problem. Any questions? Okay, good. Any questions about that? Now, what is a decision problem? A decision problem is a problem which only has yes or no as an answer. Okay? Have we dealt with any decision problems in this class so far this semester? I don't know if can you guys remember any problem that just had a yes or what?
Topological sort.
Topological sort. The topological sort of a yes or a no as an answer? Well, usually if the question was find an ordering of the vertices, then the order was what was being reported. If the question was, is a graph acyclic or not, which is something you can answer with a topological sort, that would be a decision problem. Is a graph acyclic is a decision problem. Any other decision problems we talked about in this semester? I think we had a decision problem on our last midterm. Wasn't one of those problems, given a string and a dictionary, is there a way to break that string up into express it as a concatenation of words? The answer ultimately was either yes, there is, or no, there isn't. Any optimization problem where you can say yes or no, that's good. Is a graph bipartite or not? That's a decision problem. If you say to color the vertices, that's not a yes. Decision problems are just things that return Booleans. That's exactly what a decision problem is. So decision problems arguably are a subset of all the problems in the universe. Okay? But I'm going to tell you that most interesting problems in the world that are not decision problems can still be phrased as decision problems, okay? When we want to, which capture essentially the idea, okay, of what that problem is. The theory of NP completeness is a theory about decision problems, problems that return yes and no. But it's really not a limitation, because just about any problem in the universe can, the essence of it is captured by a decision problem. Let me give you an example. What is a yes-no problem that returns, a problem that returns an answer of yes and no that captures the hardness of traveling salesman? Traveling salesman problem said, find me the cost of a minimum of the cheapest tour to visit all the vertices. Can there be a yes/no question that captures what that is the essence of traveling salesman problem? What about this thing? Given as input a graph and an integer k, does there exist a TSP solution with tour less than or equal to k? Does everybody see that this problem is a yes/no problem? This problem is something that basically either for a given graph and a given bound, integer bound k, either there's a tour of that size or there isn't. On that previous instance that I had here, okay, boop, boop, boop. If the optimal tour was of size 27, if I say, and if this is my graph G, if I said TSP, traveling salesman decision problem, okay, and I give you G and I give you 26, is there a tour of this graph at least 26? Of at most 20, cost at most 26? The answer is no. If the optimum was 27, the answer was false. If I ask, is there a traveling salesman tour of size 27 or less? The answer would be true. Does everybody see that if I have a TSP decision problem where I give myself G and a bound and I ask, is there a tour of length cost less than or equal to k? If I want to find the size of the optimal tour, could I use my decision problem to find the size of the optimal tour efficiently? Suppose I am given a graph here, and I know the total, let's say T is equal to the total edge cost. The cost of every edge in the graph. Certainly the traveling salesman tour, the optimum tour, is going to involve only n of these edges. So that's going to be a lot less than T. But the sum of the edge weights is an upper bound. 0 is a lower bound on the size of the TSP tour. If I did binary search, asking, is there a TSP tour in my graph G of size, let's say call it X. If I ask for at my total edge weight over 2, if I get a yes, if I get a true, then the tour is going to be, optimal tour is no bigger than this. If I get a false, the optimal tour is going to be bigger than this. That says there is no tour of size T over 2. That means I gotta increase it, and then I would be searching for a tour of size, maybe Tn 3n over 4. Does everybody see that it's kind of by doing a binary search on the range of possible answers, I would be able to use my yes-no problem to tell you the size of the optimal tour. Okay? Any questions about that? I don't know how many people see that or are confused or something. What is interesting? My claim here is that if I limit my attention to decision problems and only decision problems, if I can prove that decision problems are hard, almost any problem I ask that is interesting, there is a decision problem version that captures what makes it hard. So if I talk only about decision problems, I'm really talking about all the problems we have in this class. Any questions about that? Okay, so where are we so far? We have a world, we're living in a world where we're going to be concerned about how hard certain problems are. Do certain algorithm problems have fast solutions or not? Again, the input, the general thing is a problem. The actual instance is the data we feed, the parameters we feed a problem. A particular instance is a particular input or, data instance. The theory of NP completeness is going to deal with yes, no, true, false, Boolean problems. But as I will argue here, almost any interesting problem can be expressed as a decision problem. So we're going to be interested in that. Any questions about the reasoning here? Why am I going to care about decision problems? Let's see if we can figure this thing out now. Let's go back to Bandersnatch and mobility. We're going to see these slides over and over again. What does yes-no decision problems have to do with this algorithm? Bandersnatch is an algorithm problem. Mobility is a, an algorithm problem. You see, I've got this translation. What is the consequence if we limit Bandersnatch and mobility to true-false problems as opposed to general things? Can anybody see that? Maybe it's a little too hard to see still. Can anybody see that? What are the possible outputs of Bandersnatch of G? What might the answer, if Bandersnatch and mobility are decision problems, what are the possible answers of Bandersnatch of G? Could be a true or it could be a false. What is the answer of mobility going to be? If it's a decision problem, it could be a true or a false. Does everybody see that? So now maybe an algorithm for doing this, solving Bandersnatch in this way, doesn't look like quite the miracle it did before. I want to translate the input of G into an input Y such that mobility of Y is always the same as Bandersnatch of G. That means that when Bandersnatch of G is true, mobility of Y is true. And when Bandersnatch of G is false, mobility of Y is false. Okay? So the decision problem, this translation, okay, which should still seem a little bit magical, just has to preserve the answer of true and false. And that sounds like an easier job to do than translating all possible inputs to all possible other inputs. Any questions about it? That's why I'm going to care about decision problems. Any questions? So any questions at all at this point? A reduction okay, which is what we are looking for, is a transforming of an algorithm problem, one algorithm problem, to another algorithm problem, okay? And that's saying that you know how to, a reduction transforming problem A to problem B is an argument that if I know how to solve B, I know how to solve A, okay? Sometimes we can use this idea of reductions to find a fast algorithm for something. Can you guys remember back to when we did this daily problem where I asked for, does there exist? What is the shortest path in a graph G from vertex S to vertex T using exactly K edges? Does anybody remember that problem of the day? One way I solved this was by dynamic programming. But do you remember how I took this problem and translated it into a shortest path problem on a general shortest path problem? Remember, here you had your graph G. I created something which had K copies of that graph G, cleverly wired together such that the shortest path from S to T using K edges was exactly the shortest path from that S to that T. And because every edge brought us down one level, that path had to use K edges. Do people remember this? I think everybody's got their screen turned off. So I'd like some signs of life here. Remember this? I solved that problem by doing a translation. I solved that problem by doing a reduction, okay? And that is the kind of thing that this Bandersnatch-Bobilly is. What is this Bandersnatch? Got to go back to. What does that Bandersnatch-Bobilly algorithm look like? I am giving you a way to solve, okay? I am reducing the solution of Bandersnatch to the solution of Bobilly, okay? I am translating my Bandersnatch algorithm, my Bandersnatch instance into a Bobilly instance. Such a Bobilly of Y gives me Bandersnatch. In the homework problem, the problem of the day, I did an algorithm like this. This was shortest path with K edges. Okay, exactly K edges. I had G, S, T, K. And Bobilly was shortest path in a graph G, okay, from S to T. I showed that I could solve this problem by reducing it to general shortest path, okay? And in that case, I had a fast shortest path solver. So this gave me a fast shortest path of K edges solver, right? This is what I mean by a reduction. If there is a fast Bobilly solver, then there is a fast Bandersnatch solver. That was the first case over here, right? But if there is no fast, Bandersnatch algorithm possible, this is an argument that they can't be a fast algorithm for solving Bobilly. That is the logic that we are dealing with here. Any questions about that logic? Any questions about any of this reduction stuff? Any questions about what the idea of a reduction stuff is? Okay. Again, there is a story about a computer scientist and an engineer. Okay, we're sitting around the kitchen. Perhaps it's a pandemic, they can't get out of the kitchen. The engineer gets up at some point and says, I want some tea. Okay, and so what does the engineer do? The engineer goes to the shelf, okay, goes to the top of the shelf, pulls out a teapot, takes that teapot, goes to the sink, puts water in it. Okay, the computer scientist is watching this intently. Okay, they then put the teapot on the stove, turn the stove on. Okay, he waits, it whistles, it blows. The engineer goes to another cabinet, pulls out a tea bag and a cup, puts the tea bag in the cup, pours takes the teapot with the boiling water, pours it into the cup. Computer scientist is looking interestedly. A minute later, he says, I want some tea. What does the computer scientist do? He goes to the stove where there is the hot boiling pot of water that was left over. What does he do? He pours that boiling water out into the sink, dries off the key pedal, puts it on the top of the shelf again, and then says, I am done. I have reduced this to a solved problem. Okay? If you understand why that is funny, you understand what a reduction is. And if you don't understand why it's funny, either I told it bad or you don't understand what a reduction is. Any questions about that? Do you see that the computer scientist had solved the problem of making tea once he had reduced it to the way the engineer had made tea? Okay. Any questions about that? Again, I don't think I got laughs this time, but does everybody, any questions about what that story is, what a reduction is, what is Bandersnatch and mobility, what are we trying to do? Any questions? Okay. I'm willing to end a couple minutes early if there are no questions, but I want there to be some questions here about what the strategy is. Okay. Any questions? Maybe before I let you go, I'm going to take one last look. I don't know why I finished so fast today. Okay. What is the idea here? The key critical idea to make sure that you understand this. If I have an algorithm like this that solves a decision problem, Bandersnatch of G, this is a decision problem, by translating the input into a different format, the input for the mobility problem, and then calls a mobility solver, where mobility is also a decision problem. And it did this translation, this conversion, in a very, very special way. So mobility of Y is equal to Bandersnatch of G. If we did that translation in a way that preserves the answer, and that translation is fast, took order n time, n squared time, n cubed time, n to the 100th time, I'm still going to count that as fast enough. If I have a fast translation, what does that mean? If there was a fast mobility solver, the time it took mobility on the translated input plus the translation time would be the time of this Bandersnatch algorithm. But if instead of having a fast algorithm for mobility, all I have is a guarantee that there is no possible fast way to solve Bandersnatch, okay, then what this algorithm proves is there is no possible way to solve mobility quickly. Because if I could solve mobility quickly, I solve Bandersnatch quickly. And there is no way to solve Bandersnatch quickly. Any questions about any of this stuff?
Could you explain with this story the problem that the computer scientist solved?
Okay, you're saying you didn't laugh when I told you the story about the computer scientist and the tea. You want to get that joke so you can tell it to someone else.
I do.
Okay, so what is the story? We are in a kitchen. Okay, there is a stove. Okay, there is a shelf. On the shelf is a teapot. I guess that's a teapot for my purposes. Okay, on another shelf, there are tea bags. Okay, and there is a cup. Now, from this state, the engineer, we'll make the engineer look like this, okay? The engineer, okay, makes tea by taking the, teapot down, adding water to the teapot, turning on the stove, okay? Pulling down the cup, putting in the tea bag, taking the hot water and putting this thing in, and then putting the tea kettle back there. That is what the engineer did. The computer scientist is trying desperately to figure out, how do you make tea? You have the puzzled looking computer scientist. How can I make tea from this situation? They've never seen it before, right? But what does he realize? I have watched the engineer make tea. When the engineer made tea, what did he have? He had a teapot up here. He had a tea bags over here. He had a cup here. How can the computer scientist make tea? He realizes, this is great. I will pour out the hot water because the kettle started empty. I will dry off that kettle and move it up there. I will take this cup that the engineer was drinking from, and I will clean that cup and dry it and put that cup back on the shelf. And then put the tea bags back where they are. Now I know how to make tea, because this is exactly what it was. I can reduce it to the exact set of steps the engineer used to make tea. Okay? If you can think like that, you understand the idea of a reduction. Okay? And you can understand the case of making problems harder than they perhaps need to be. Okay? Now, NP completeness, we're revealing how hard the problems are, not making them hard. Any questions about that? Okay? And the computer scientist never got his tea, basically. He was content once he had figured it out, he was okay. Any questions? But if he really was desperate for the tea, he could now make the tea. Any questions about that?
Oh, yeah, I had a question. I just wanted to clarify what you were saying about the computer scientist at the end. So could you sort of look at it as if the process that the engineer did was the algorithm, and then the computer science putting the stuff back at the end was simply like the cost of reduction? And so at the end, you sort of...
Let's go back to the this thing. Let's do the Bandersnatch Bobilly look of the engineer and the tea. What is the Bobilly? It seems to me that here, Bobilly of Y is the engineer's T algorithm from the initial state. Does everybody see that that's what Bobilly is? What is Bandersnatch? We want to solve the CS solution from the current state. How can the engineer, what does the engineer do to finish his algorithm? He constructs a procedure to translate the current state to what the engineer needs, right? The input that the engineer needed. The engineer seemingly needed the tea kettle on the shelf. They needed the teacup in the pantry. Okay? So the translation of the state that we're given now to the state that the engineer used, that is this translation. That is the actual reduction. And once the engineer figured this, once the CS person figured this out, Okay, they knew how to make T. Okay, any questions about that? Okay, any questions? Yes.
Was the last part of the joke, like, could you add on, like, say, like, after the computer scientist put away all the things, he asked the engineer to make him tea? Like, I feel like is that kind of the way it goes?
Well, okay, so what
Because
I would
the
say is
last
the
part of that is
computer
return the
scientist,
answer of
okay, so
mobility.
should he have demanded, okay, if he could succeed in then telling the engineer to make T, he's even better off. But that's kind of not what the argument here is, that we are solving the problem of how do I make T from the current range. I am reducing that to how did I make T from the original state, right? The engineer knew how to make T from the original state. Okay, I want to solve the problem, okay, of how do I make T from a world where the tea kettle is on the stove. Okay, if I could translate, if I knew a way to make it from when everything was put away, then I could translate my original problem to the problem of where everything is putting away by simply cleaning it up. Okay, and so the reduction here is the act of cleaning up. The mobility is the procedure developed by the engineer after no doubt years of study to make T. Okay, and this Bandersnatch algorithm was the computer scientist's insight of how I can also make T. Okay, when confronted with the messy kitchen. Any questions about that? Okay, think about it. Okay, perhaps not that much, okay, but think about what the argument here is, okay, about why, if in fact, okay, the engineer had said, oh, I know how to make T. If the computer scientist had instead went to the engineer and said, I know how to make T, okay, if you know how to make T, once the kettle is on the shelf and cups are put away, I know if you know how to do that, I can take our current kitchen and reduce it to that state. Then we could have T. Okay. Now, if the engineer then said, but there's no possible way to make T when the tea kettle is on the shelf, then basically what the engineer would be proving, what the computer scientist would have proven here, is there was no possible way to make T from the messy kitchen. Okay. If you understand this analogy, that's good. If it's confusing to you, don't let it confuse you. Think about what this algorithm means. We're going to see more of that next class. We're going to see these Bandersnatch mobility slides for the rest of the semester, every single class. Okay, but next time, instead of trying to make T, we're going to start trying to talk about what problems are hard and how to actually do a reduction. Any questions about that? Any questions? Okay, very good. Okay, I'll talk to you guys next class then. Actually, you know what? Wait, okay, I'm sorry about this. Let me do one last thing, which is maybe now I think I figured out why I why I did not have time for this. Why I had time. Now I think I figured it out. I promise I will end quickly, what you call it. But I wanted to show you one thing, okay? I'm not going to give you this review. I'm going to tell you about what is the mother of all hard problems. I just want to introduce this to you quickly, okay? This whole reduction thing, if I'm going to start to argue that something is hard, I need to have a problem that I can guarantee you is hard. This reduction thing, if I'm going to use it to prove problems hard, I need to be able to have a Bandersnatch that I can say there is no possible fast way to do it. What is going to be my Bandersnatch? There is a famous problem called satisfiability, and I'm just going to introduce it, but we're going to have to live with this for a while. So I'll introduce it again later, but it's good to look at it. Satisfiability is a logic problem. It takes as input a set of variables. Logical variables can be true and false. And it creates a set of logical clauses on them. A clause is a set of variables with a negation on it. Each clause is going to be interpreted as the logic expression. This is going to be V1 or not V2. This clause is going to be, actually, let me move it slightly. This clause here is going to be not V1 or V2. And I'm going to put an and for the comma. Does everybody see this Boolean language clause? Let's write it again. V1 or not V2. And V1, not V1 or V2. The satisfiability question asks, is there a way to make a true and a false to assign to V1 and V2 such that this expression is true? Can anybody look at this expression and find an assignment of values to V1 and V2, variables V1 and V2, such that this statement is true? Is there a way to make this logical expression true? What if V1 was true and V2 was true? What is true or what is not true?
True.
False.
Not true is false. What's true or false?
True.
True. And what is not true? Not
False.
true is false. False or true? What is that?
True.
True.
True. True and true is true. Is that correct? So in this expression, you can make this expression true by setting V1 equal to V2, both being true. Is there any other way to make this expression true?
Make both false.
If I make them false, false. False or not false is going to be true, right? And not false is true, true or false is true. Does everybody see that there are two different ways you can satisfy this expression? You could kind of imagine, let's say there was a hypothetical president who said statements that were not obviously true. Okay? You can imagine them having a staff after the words, trying to find, is there a way that this statement was true? And they said, yes. Well, you note that if we set V1 to be this and V2 to be that and V3 to be that, the statement is true. Satisfiability is saying, find a way to make the statement true if it's possible. What if I have an expression like this, which is we read V1 or V2 and V1 or not V2 or V1? Is there a way to make this statement true? Oh, this is not an or, this is an and. Excuse me, that's important. Is there a way to make this statement true? Any possible way to make this true? There's 4 possible ways of doing the logic, right? V1 can be true and false, V2 could be true and false. I can argue there is no possible way to make this thing true. Why? If it is going to be true, what do we know? If the whole statement is true, what do we know about V1?
It's
V1 had better be true, right? If V1 is true, what do we know about not V1? V2. What do we, oh wait, what did I
think
do?
the last one should be not V1.
Not V1. Oh, okay. If it's not V1, I'll give you another chance. What do we know about if it's the last thing is not V1? What do we know about this last clause? How do we satisfy it? What must
V1
V1 be equal to?
must be false.
V1 equals false. If V1 is false, this is going to go away, right? What do we know about V2? To save this, if it's an and of these clauses, what must we do?
V2 must be false.
V2 must be equal to false. And what do we now do? We've got false or false, and this expression cannot be satisfied. Certain logic expressions can be satisfied. This one can't. Certain logic expressions can be satisfied. Certain logic expressions cannot be satisfied. The satisfiability problem takes as input a logic expression and says, yes, there's a way to make it true, or no, there is no way to make it true. And the satisfiability problem is, given a logic expression, is there a way to make it true? If you had an algorithm, that is the mother of all hard problems. Okay? I will later try to convince you of this a little bit more, but for now, I need you to trust me that this is a problem for which there is no fast algorithm for. And if there is no fast algorithm for it, then what does that mean? That means we can have this thing play the role in Bandersnatch. Okay? And then we can maybe try to prove that other problems are hard. Okay? Using this idea. Any questions? I did that very fast. Try to review what the satisfiability problem is for next time, so you'll be fluent in it, and I look forward to talking to you about things then. Anything else?